Imagine a landscape completely deprived of water. The earth fractures, the terrain hardens, and the environment becomes entirely hostile to new information. This physical desolation is precisely what happens inside the human mouth during ageusia. In clinical terms, gustatory failure operates on a spectrum. At one extreme is ageusia, the absolute, complete loss of taste. Closely related is dysgeusia, where the perception of taste is severely distorted, turning ordinary flavors into foul, metallic, or rotten sensations. These extreme symptoms are highly prevalent in patients suffering from severe dryness of the mouth and eyes, a clinical state known as sicca. This presents a diagnostic paradox. Patients diagnosed with primary Sjögren syndrome possess specific systemic autoimmune biomarkers that explain their sicca symptoms. However, a parallel group of non-Sjögren sicca patients lack these markers entirely, yet they suffer the exact same collapse of their sense of taste. Gustation functions as strictly interdependent pipeline, requiring three distinct components to work in unison: a solvent, a sensor, and a neural pathway. To understand why these patients lose their sense of taste, we have to look at the individual failure points within that pipeline and isolate where the system breaks down. We begin with the sensor node. The bedrock axiom here is that human taste receptors require precise chemical thresholds to activate. For sour taste perception, researchers have identified an absolute biological threshold. The human tongue requires a pure, free hydrogen concentration of 0.575 millimoles per liter, which corresponds to a pH of exactly 3.24. This chart shows lemon juice added to a neutral solvent, creating a rapid initial drop in pH. Notice how the curve flattens out. As it approaches the 3.24 perception threshold, the drop tapers off. It requires exponentially more acid to lower the pH further. But equating a low pH directly to the subjective experience of sourness is an incomplete reading of the chemistry. This chart of common drinks shows pink lemonade and cranberry juice share near identical pH levels, around 2.5, yet elicit distinct tastes. The difference lies in anionic acid species. These molecules don't produce sourness themselves, but interact with hydrogen ions to alter the perceived flavor. This chemical complexity is why engineers developing synthetic electronic tongues cannot rely on single chemical detectors. Instead, they must use broad arrays of nonspecific sensors combined with complex pattern recognition algorithms. Specific chemical thresholds are biologically required, but they are useless if the complex chemical pattern cannot be read by the sensor array. Those chemical sensors, however, are entirely blind without a liquid medium. Taste buds are protected by a tight junction. Fluid must transport tastins through this barrier. Saliva acts as this active solvent. It uses amylase to predigest starches into simple sugars and bicarbonate buffers to interact with free hydrogen, modulating high acidity before sensor contact. The body tightly regulates this environment through unstimulated and stimulated salivary flow rates. Because high acidity can damage oral tissues, sour stimuli naturally command the highest stimulated flow response to flush and protect the system. Saliva is the active electrochemical bridge. If you remove the solvent, the data transmission from the food to the sensor is physically severed. Imagine a highly viscous, depleted fluid struggling to bridge a critical cellular synaptic gap, stretching thinner and thinner before snapping. This exact mechanical failure defines the clinical realities of both primary Sjögren's and non-Sjögren sicca patients. Comparing unstimulated whole saliva secretion rates reveals a severe pathological drop in baseline flow for both primary Sjögren's and non-Sjögren's cohorts. The normal threshold is 0.1 milliliters per minute. Strikingly, over 59% of non-SS and 74% of key SS patients fall completely below this critical line. Tracking objective gustatory function shows that as the solvent fails, sensory function fails alongside it. Measured taste scores plummet in tandem with the drop in saliva production. For non-SS patients, this triggers a subjective nightmare. 77.3% report severe dysgeusia, living with constant taste distortion. The nature of that distortion is highly specific. Over 63% of these patients experience a persistent, lingering metallic taste. a direct misfire of isolated sensors lacking their proper solvent buffer. Despite lacking the formal autoimmune markers for Sjögren syndrome, the clinical data proves that non-SS patients suffer a statistically equivalent solvent and sensory collapse. The third and final node of the gustatory pipeline is the physical wiring required to transmit the electrochemical data to the brain. The facial, glossopharyngeal, and vagus cranial nerves carry signals directly from the tongue's taste buds to the medulla solitary nucleus. After processing these impulses, the brain utilizes a profuse projection network, mapping taste data out to the amygdala and hypothalamus. Because this neural redundancy is so robust, complete true ageusia is statistically very rare compared to partial loss or distortion. Severing this transmission usually requires profound, systemic structural damage. In patients receiving radiotherapy for head and neck cancers, the radiation systematically destroys this wiring. It directly injures the neural pathways while simultaneously destroying the salivary glands. A perfectly balanced solvent and a highly sensitive receptor array mean nothing if the physical neural cable to the brain is severed. When we pull back and look at the entire gustatory pipeline, solvent, sensor, and pathway, the clinical reality of sicca patients becomes clear. If we overlay the non-SS patient data onto this model, the solvent node flashes red. The chain is broken at the very first step. A failure at the solvent stage effectively blindfolds completely intact receptors, and by blinding those receptors, it functionally unclogs an otherwise healthy neural pathway. Yet the diagnostic paradox remains. Because non-SS patients test negative for Rho and Law autoantibodies, they are frequently excluded from a primary Sjögren's diagnosis, leaving their debilitating symptoms unclassified. It is the biological equivalent of a powerful engine violently seizing up simply because a single fluid line runs dry. Gustatory dysfunction must be treated as a systemic biomechanical failure. The absence of a specific autoimmune biomarker does not negate the reality of a collapsed chemosensory pipeline.